yesterday we talked about what the properties were that made a parallelogram a quadrilateral. So to review that, um, our properties of parallelograms, we have several. First, the definition. By the definition, a parallelogram is a quadrilateral with two sets of parallel sides. Then Theorem 8.2 told us that parallelograms have opposite sides that are congruent. 8.3 told us that the opposite angles are congruent in a parallelogram. 8.4 told us that our consecutive angles are supplementary, so that angle 1 plus angle 2 is going to equal 180. And Theorem 8.5 told me that my diagonals are going to bisect each other. So using these properties, we're going to look at some new theorems today that are going to help us prove that if we have a quadrilateral, we can prove that it is a parallelogram. So let's start looking at these theorems. So Theorem 8.6 is the converse of 8.2. So if both pairs of opposite sides are congruent, then that's going to make it a parallelogram. 8.7 corresponds to 8.3, so opposite angles are congruent, so the quadrilateral will be a parallelogram. 8.8 corresponds to 8.4, so if the consecutive angles on both sides are supplementary to an angle, then it will make it a quadrilateral. 8.9 corresponds to Theorem 8.5, which says that diagonals bisect. So if your diagonals bisect each other, then it's a parallelogram. And then our new one is that if you have one set of opposite sides that are both congruent and parallel, then it will be a parallelogram. This is because the other sides are going to have to follow suit, and they will also have those same properties. So let's look at some examples. And it says, use the definition of parallelogram to prove that the quadrilateral is a parallelogram. So if we look at this, the definition of parallelogram says two sets of parallel sides. So what we need to do is figure out if sides are parallel, which means that we will need to use slope. So if we can prove that they aren't parallel, then we can prove that it's not a parallelogram. So first, let's choose two sides. Say that we choose HI and GJ. So if we choose these two sides and we want to find their slopes, the slope formula is y2 minus y1 over x2 minus x1. So I'll take my second y, which is 6, and subtract my first y, which is 1, and put that over my second x minus my first x. So when I do this, I get 5 over negative 1, which is a slope of negative 5. So if this is a parallelogram, the slope of this side also needs to be negative 5. So we're going to follow those same steps, and we'll do 6 minus 1 over negative 1 minus negative 3. So here I will get a slope of 5 over 2. So notice that our slopes do not match. Therefore, we don't have two sets of parallel sides if we don't even have one. So we're going to say that HI and GJ are not parallel. So to show that, we use the parallel sign with a slash through it. So since these are not parallel, GHIJ is not a parallelogram. So since it told us to prove it and we weren't able to, we can prove that it's not a parallelogram. It doesn't have that condition where the opposite sides are parallel. On example 2, we have another quadrilateral, and this one says use Theorem 8.6. So if we go back and look at Theorem 8.6, this one says that opposite sides are congruent. So to use this, to figure out if they're congruent, we're going to have to use distance. So we can use the distance formula, which says that the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. Or remember that this formula comes from Pythagorean theorem. So Pythagorean theorem says a squared plus b squared equals c squared. So we can add our horizontal length squared to our vertical length squared and also find those numbers. So let's think about it in terms of Pythagorean theorem. So if I look at the difference in my x to go from 1 to 4, that's 3. So that'll be 3 squared for that horizontal length. Then my vertical length is going to go from 1 to 4, so that's 3 as well. So 3 squared is 9. 9 plus 9 is 18. So we want to put this radical into simplest form. And if we want to put it into simplest form, we need to find a perfect square that can go into this number. So remember, perfect squares are numbers that come from multiplying something by itself. So our perfect squares are 4, 9, 16, and 25. So now 25 is bigger than 18. I'm not going to go further than that. So I look, 4 can't go into 18, but 9 can. So I can rewrite this as the square root of 9 times the square root of 2. So since I know that 9 is a perfect square, I can go in and reduce that. So the square root of 18 is the same thing as 3 root 2. So the length of QR is 3 root 2. If this is going to be a parallelogram, then this other side has to have the same length. So we're going to look at side PS and see if it has the same length. If it does, then we can go on to QP and RS. If not, then we can prove that it's not a parallelogram. So using that same method, I'm going to find distances. So negative 2 to 1, that's 3 numbers. So we're going to start with 3 squared. 2 to 4, that's 2 numbers, so that's 2 squared. So 3 squared is 9, 2 squared is 4, 9 plus 4 is 13. So if we look at our list of perfect squares, 4 can't go into 13, 9 can't go into 13, and 16 is too big. So square root of 13 is as big as we can go. So since square root of 13 and 3 square root of 2 are not the same thing, segment QR is not congruent to segment PS. So PQRS is not a parallelogram. So if our first set of sides is not congruent, then we can't have opposite sides, both sets being congruent, so it can't be a parallelogram. So for example 3, this one says use theorem 810. So theorem 810 said that we have one set of opposite sides, and that set of opposite sides has to be both congruent and parallel. So we need to use distance and slope on this one. So I tend to think that slope is a little bit easier to find, so let's make sure that they are parallel before we go into the distance formula. So for slope of xy, I'm going to do 5 minus 2 over 1 minus 4, which will give me 3 over negative 3. And 3 over negative 3 reduces to negative 1. So my slope is negative 1. If the slope of this line is also negative 1, then we can move on. Then here we have 2 minus negative 1 over 0 minus 3. So 2 minus negative 1 is 3 over negative 3. So that also gives me a slope of negative 1. So with this, I can tell that this set of sides is parallel. So to prove that this is a parallelogram, I need these to also be congruent if I'm going to use 810. So we got that our slopes are the same. Now let's check our distances. So for my horizontal piece to go from 4 to 1, that's 3 numbers. And to go from 2 to 5, that's also 3. So that's 9 plus 9, which is 18. So we've already reduced this radical in the previous problem, and we know that that reduces to 3 radical 2, because 3 is the square root of 9, and 9 times 2 is 18. So we need this other one to be the same. So for this one, I have a horizontal distance from 3 to 0, so that's 3 numbers. A vertical distance from -1 to 2, and that's 3 numbers. So under the radical, we can tell that this one's going to end up the same. So we have parallel lines that are also congruent. Therefore, since xy is parallel to wz and xy is congruent to wz, since we have both of these conditions by theorem 8.10, we can say wxyz is a parallelogram. Of course, if this question had just said prove the quadrilateral is a parallelogram, we could have used a variety of methods. So just since this one said 8.10, that's why we had to do this method. Moving on, we're going to look at a couple proofs. So here's our first proof. We have that triangle PQT is congruent to RST, and we need to prove that this is a parallelogram. So since this just says prove it, we have several ways. Let's try to use a method that we haven't used yet. Let's see if we can do it by 8.9. So if I want to prove this one by 8.9, that means that I need my diagonals to bisect each other. So the definition of bisector is that it cuts something into 2 congruent parts. So if we start off with PQT and RST, that's our given. And from our previous unit, we know that whenever we have congruent triangles, we're going to try to use CPCTC. So CPCTC means corresponding parts of congruent triangles are congruent. So that means that any of these corresponding parts can be congruent. So the pieces that are going to be useful to me if I want to use 8.9 are the pieces that are part of the bisector. So I'm looking at PT and TR, and let's see if we can make that congruent. So looking at how they're named, we can use PT, and then TR, even though it's named the other way, those are part of the triangles. So just naming it by how the triangles are named, that would be PT is congruent to RT, going first to last, and that's going to be by CPCTC. So let's go and mark those. So we have one bisector at T. Right now we can say that point T is a bisector, or a midpoint. Next we're going to look at that other diagonal. So this is like ST and TQ. So if I look here, I have QT, and with that is ST. So we're going to name them like the triangle named them. So QT is congruent to ST, and that is by CPCTC as well. Still using those congruent triangles. And if I mark those, now I have that both of my diagonals are bisected. So that's what I need to say in my next statement. So that will say, we're going to use the whole segment, PR and SQ bisect each other. And since bisecting means that it cuts into 2 congruent parts, that's the definition. So remember that the definition is biconditional. It can be used to say that a bisector cuts it into 2 congruent parts, or if it's in 2 congruent parts, it can be used to go back to say it's a bisector. So this is the definition of bisector. So now that we have that our diagonals bisect each other, we can use theorem 8, 9 to prove that it is a parallelogram. All right, so for our final proof, here we're given that angle 1 is congruent to angle 2, and that triangle IJK is congruent to LMH. So starting off with angle 1 is congruent to angle 2, that's given. And what I want to do is I want to try to figure out how to do this. So if I have these two, this one is inside the parallelogram that I'm trying to prove. This one's outside, so this angle doesn't help me much. I need to figure out a way to get something to do with the parallelogram. So what I do see is that if I extend these sides of the parallelogram, or this figure right here, if I extend it, notice that it is two parallel lines, or what we suspect to be parallel lines, in a transversal. So if I think about this set of angles, those are in the same place on different lines. Those are corresponding angles. So if I can prove that, since I already have that these angles are congruent, I can use the converse of the corresponding angles postulate to say that the lines are parallel. So the pair is corresponding. And since I'm proving parallel, it is the converse. And so my statement is going to be that HL is congruent to IK. Or if I said congruent, I meant parallel. So HL is parallel to IK. So now we either have to think about, we either need two sets of opposite sides that are parallel, or we need two sets of opposite sides that are congruent. So since I have this triangle still that I haven't used, let's see if CPCTC can help us. So IJK to LMH. So if I look at these lines that are already parallel, if I can prove that those lines are also congruent, then I can say that it's a parallelogram. And I'm able to say that because of CPCTC. So if I want to name this one, HL like I did previously, that's last to first. So HL. And then on the other side, I'm just going to name it like the triangles say. So last to first, KI, and I'm going to say that those are congruent. And the reason I can do that is because of those congruent triangles. So now that I have parallel lines that are also congruent, that leads me to theorem 8, 10. So that's how we use our previous units to say that we have a quadrilateral that is a parallelogram.